Welcome to the seventh set of presentations in the second webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees, their families, and their colleagues are safe amid the ongoing COVID-19 pandemic. We thank everyone for attending the webinar today. The webinar series, which began in the spring of 2020 and then restarted last autumn, has been an immense success, and the recordings of those webinars continue to be viewed on YouTube. We plan to continue these webinars through the present academic year with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Subsequent webinars will be announced on the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Nicholas Carente and Shivam Parashar, PhD students at Rutgers University, and Klaus Richard, a PhD student at Universidade Federal do Ceará. These students were Best Poster Award recipients at the inaugural IAS Twitter Poster Conference. I am Nicholas Wilkins at the University of Alberta and the IAS Student Education Committee. Today's webinar will be moderated by David Donacci of Imperial College London in the United Kingdom. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you have not already. Our dues are minimal, only $20 US per year to support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @intadsos for future updates regarding IAS events, webinars, and information about scientific meetings. Please help expand our YouTube channel by subscribing. We would like to remind the viewers of the upcoming Fundamentals of Adsorption Conference in Broomfield, Colorado, between May 22nd and 27th, 2022. More information can be found on the website given in the slide. The presentations given in today's webinar are by the recipients of the Best Poster Award in the inaugural IAS Twitter Poster Conference, which was held between the 7th and 11th of December 2020. The 5 recipients were chosen by a committee of judges, most of which are members of the IAS Education Committee. All 5 recipients were invited and have agreed to give talks in the July and August webinars. The awards were funded by the IAS and the Georgia Tech Separation Center. And now I'll hand it off to David to introduce our first speaker today.
Shivam Parashar is a PhD student in the Department of Chemical and Biochemical Engineering at Rutgers University in the United States. He is also supervised by Dr. Alexander Niemark. He expects to graduate in the summer of 2023. Shivam completed his bachelor's degree in chemical engineering at the Indian Institute of Technology in Roorkee, India in 2018. His research interests include computational modeling and molecular simulation of gas adsorption on nanomaterials. With that, I'd like to welcome Shivam to begin his presentation.
Hi, good morning, everyone. First, I would like to thank David for this introduction and also IAS for inviting me to present my talk today. So, I'm Shivam Parashar, and I'm a PhD student working with Dr. Nema at Rutgers University. And today I'll be talking about Pore level decomposition of adsorption isotherms for characterization of metal organic frameworks. So, okay, to characterize nanoporous materials, gas adsorption is a very commonly used method. And for that, argon, nitrogen, and CO2 are used as adsorbate probes at their normal boiling temperatures to get an adsorption isotherm. An adsorption isotherm is a plot between the volume of gas adsorbed on these materials versus the relative pressure of the gas phase. And from these adsorption isotherms, several properties of these materials can be calculated, such as the isosteric heat, which is the heat released during the adsorption, surface area, which can be calculated using the BET method, which gives surface area based on monolayer formation, and pore size distribution using methods such as density functional theory and the BJH. So I'll talk about how pore size distributions can be calculated from an adsorption isotherm. So usually nanoporous material have a distribution of pore sizes, and therefore their experimental isotherm can often be expressed in terms of the integral of the pore size distribution function, phi d, and the kernel k. The kernel is a set of theoretical isotherms which are computed at different pore diameters, but on a specified pore geometry, which is usually a sphere, a cylinder, or a slit type pore. So given the kernel of theoretical isotherms and the experimental isotherm of a sample, we can determine the pore size distribution function by solving this adsorption integral equation. In this example of CMK3 carbon, this experimental isotherm can be reconstructed from the kernel of theoretical isotherm by using this pore size distribution. From this, we know that the sample contains two types of pores of sizes 2 and 5 nanometers. Density functional theory is a well-established approach to model confined fluids and to calculate those kernels. So given the interatomic potentials between the solid fluid and fluid, the equilibrium state of this system can be determined by minimization of this grand thermodynamic potential omega, which is assumed to be a functional of the fluid density rho of r. And by solving this equation, we can determine the fluid density within this pore. And by integrating it, we can get 1 point of this adsorption isotherm. So by repeating this process at different chemical potentials or pressure, we can determine this complete isotherm. To determine the kernel, this whole process has to be repeated again at different pore diameters. So we'll get these theoretical isotherms at different pore diameters, which is called a kernel. So density functional theory works beautifully for materials such as carbon, silicas, and zeolites. And it is also a recommended method for determining pore size distribution by the IUPAC. But in certain cases of MOFs, it does not work so well. One such example is PCN224, which has two types of pores of sizes 17 and 25 angstroms. But when we use a kernel to fit the GCMC isotherm, we get just one peak at 25, and it misses a peak at 70. Similar is true for the SIF 412 MOF, which has three types of pores, but DFT misses one peak at 15 angstroms. So these discrepancies between the geometric sizes and the DFT pore sizes are because these kernels were computed on a simplified pore geometry, which was either a sphere, a cylinder, or a slit type pore. Whereas metal organic frameworks are interconnected network of channels and cages, and their pores may not have any well-defined pore geometry. So we need a new method of pore structure characterization for MOFs that considers their realistic pore geometries. Another motivation of this work is to identify defects within nanoporous materials. So practically all metal organic framework samples are non-ideal crystals, and they may contain defects that block the pore network space. So these defects may be introduced during the method of preparation or during the activation of the sample. For example, when synthesizing this copper BTC MOF using two different methods, hydrothermal and microwave assist methods, we see that the isotherms are significantly different, although their XRD patterns are quite similar. So these defects may be introduced during the method of preparation or activation of sample. In both cases, so the objectives of the study is to quantify these defects and MOFs using adsorption, and to measure up to what extent individual pores of these MOFs are accessible for adsorption. So these questions are related but cannot be answered by currently available methods. So we propose as a solution to obtain adsorption isotherms in individual pores. For that, consider this example in which I show a snapshot of a hypothetical MOF, in which we can see that total of 10 molecules are adsorbed, and we show this state as one point in this adsorption aspect. Now we divide the unit cell into two pores, pore A and pore B, and realize that there are 6 molecules in pore A and 4 molecules in pore B. And we show the states of individual pores by decomposing this total isotherm into two isothems, which we refer to as fingerprint isothems. So these fingerprint isotherms can then be used as a kernel to fit the experimental isotherm, and we can determine these weights phi I. So these phi I represents the accessibility of the ith pore. As an example, when we consider an ideal sample, experimental sample, and we use these kernels, these fingerprint isotherms as kernels to fit the experimental isotherm, we should get 100% pore accessibility for both types of pores. To demonstrate this approach, we consider one example, PCN224 MOF, which is made up of zirconium clusters and porphyrin rings. And it contains two types of pores, intersection pore of size 2.5 nanometers, which is shown in green cube, and this channel pore of size 1.7 nanometers, which is shown in the yellow cube. If we talk about its geometric pore size distribution, it has 3 peaks in it, 2 of which corresponds to these individual pores, and the one at the center corresponds to the window connecting the two. So whenever we calculate geometric pore size distribution for any material, and we encounter, say, n peaks in it, it doesn't necessarily mean that there are n different types of pores. It just means that there are n different diameters of spheres that can be fitted within the MOF, and these spheres may overlap with each other, and that is what is happening here. So this is a window connecting the two cages. So then we simulate argon at 87 Kelvin on PCN224 MOF. On the left is the total adsorption isotherm in linear and logarithmic scale of pressure. On the center, we show the snapshot of adsorption, and on the right is how we construct the fingerprint isotherms. So as the pressure is increased, we see that the smaller channel pore starts getting filled, which is followed by the filling of the larger intersection pore. So what we do is we simply count the number of atoms in each of these cages, and we plot it here to construct the fingerprint isotherms. To summarize the pore filling, the channel pore fills at pressures below 0.13 P over P naught, and the intersection pore fills between the pressure and the relative pressures of 0.02 and 0.16. Recently, Cho and co-workers were the first experimental group to decompose their isotherm into two isotherms that corresponds to these individual pores, which they refer to as sub-isotherms. So this gave us a very good opportunity to compare our results against them. So here I plot experimental data alongside the simulation data, and we see that that there's a difference in the adsorption capacity and also in the shape of the isotherm. So what we do next is we multiply our fingerprint isotherms by these factors. So I multiply the fingerprint isotherm of intersection pore by 0.62 and that of channel pore by 0.58. And now we see that these fingerprint isotherms matches exactly with experimental sub-isotherms for both these pores, and also this total isotherm matches really well with experiments. So these factors are pore accessibility. So this represents that 62% of the intersection pores were accessible for argon adsorption on PCN224 in the real sample, and similarly 58% of the channel pores were accessible for argon in the PCN224 sample. Next, we show the argon adsorption density profile. So we measure that in two different directions, shown by this red and blue arrows, which are shown here. So we see that at a particular pressure, which is shown by one color, the density inside the channel pore is always greater than the density in the intersection pore along both the directions. This is because of a smaller size of the channel pore. Secondly, as we increase the pressure, we see how the adsorption, like how both the pores get filled. So channel pores fills continuously, whereas the intersection pore fills by the mechanism of capillary condensation. So we compare this similar density profile to experiments, and we get a good correspondence. So this more detailed comparison with of density profiles confirms our relevance with the experiments. So as we have seen this analysis, our approach have been applied to argon. We do a similar analysis for other adsorbents such as nitrogen and CO2 at the novel boiling temperatures. And again, we get a really good agreement with experimental isotherms for both the cases. And by matching the fingerprint isotherms to the experimental data, we calculate these accessibility factors, which are summarized in this Pore type distribution function, which is plotted for all these adsorbents, argon, nitrogen, and CO2. So again, these numbers signify the percentage of pore that are accessible within the real sample of PCN224 for all of these adsorbents. And these numbers are different for each of them. Maximum for CO2, followed by nitrogen and argon. This is because of higher temperature of adsorption of CO2 and smaller kinetic diameter. So to summarize this presentation, we developed an approach to decompose the total isotherm into isotherms that correspond to individual pores, which we refer to as the fingerprint isotherms. We compare our results with experiments for PCN224 and get an excellent agreement. And based on this matching, we calculate the accessibility factors for different adsorbents, argon, nitrogen, and CO2, and we plot it in terms of pore type distribution. So all of the results that I've shown today are well summarized in this paper, which we recently got published in May 2021. And so this method is also applicable to a family of other MOFs. And in this paper, there is another example of ZIP 412 that you can also see. There are other articles from our group which can also be referred. With that, I would like to thank all the authors in this work, especially my advisor, Dr. Nemak, and all the group members for their constant support. This project was funded by NSF, and I would like to also acknowledge computing resources from Rutgers School of Engineering and XC. With that, I would like to thank you all for listening to this presentation, and you can ask me any questions now, or you can email me later at this email address. Thank you.
Thank you very much, Shivam, for your nice talk. We have a couple of questions from Nicholas Wilkins. The first one is you kind of introduced the different kind of pore types. So in this figure, actually, have pore A and pore B. Yeah. Can they be treated, for example, as a dual-site Langmuir isotherm, or if you had 3 types of pores, could it be a 3-site Langmuir isotherm, and so on? Is it sensible to think of it in that way?
That is a good idea, I think, but I'm not sure whether the fingerprint isotherm would fit to the Langmuir model or not, because like Langmuir is a very simplified model, so it might be possible that we can fit it to maybe a model that has more number of parameters. Yeah, and then we can determine the kernels to match the experimental isotherm with. Right.
So in effect, it is determined by whether you can find an isotherm model that fits the kernel isotherm.
Yeah, but it's not necessary to do that since so this is not necessary to actually. So we don't fit the fingerprint isotherms to a model of adsorption isotherm such as a Langmuir model. We just determine it from DCMC simulations, and that makes it really accurate.
Yeah, sure. Thank you. We have a question through Zoom from Diana Azevedo, and her question is, I wonder if this approach may also be applied to other crystalline materials such as zeolites.
Yes, I would say yes, because they also have different types of pores in it, and if so the only problem is to distinguish where the boundaries of this pore will be. If you can do that, which could be easy for some MOFs, which could be difficult for others. So if we can do it, then yeah, it is easier to make these fingerprint isotherms and use them as a kernel to fit the experiment data.
Okay, thank you. And a question from me. So with this method, you've shown a way, or there is a way to calculate the pore accessibility, or that is the, in a way, the final outcome. Does that mean that is a potentially more reliable way to calculate the void volume of a given sample, the voidage? Because currently, when you're doing, process simulation or other kind of application-based modeling, you need to know the pore volume or the accessible voidage. And right now, we do that through, mercury porosimetry or gravimetric helium buoyancy measurements or helium pycnometry or some combination of those techniques. But of course, your gas in your application, maybe CO2, methane, nitrogen, may not necessarily have the same accessibility as helium.
Yeah.
So do you think this approach could potentially be used to give you a more accurate void fraction estimate of your sample?
Yes, I think yes, because so what we plot here is the pore volume itself, and we compare it with the simulations. So in simulations, since all the structures are ideal, like the pore space is available and there are no defects in it. In experiments, there are defects, so we can measure and compare like the pore, the void fractions of simulations and experiments by this analysis, and then we can determine the pore volume or the void fractions of the experimental sample more accurate.
Cool. Thank you very much. Thank you again for your presentation. If there are any more questions for Shivam, please leave them in the Zoom Q&A tab or in the YouTube live chat, or feel free to email him like you mentioned.
Right. Thank you, Nicholas, Shivam, and Klaus for your presentations. We also thank all of our attendees for joining this webinar. We hope it was both educational and enjoyable. An edited version of this webinar will be posted to the IAS YouTube channel with an announcement on the IAS Twitter feed. The hope is that the work discussed today will be a useful resource for the adsorption science community in the future. The next IAS webinar will be given by Hideki Tanaka in September. Announcements regarding the upcoming webinar and other IAS online events will be posted on our Twitter feed and throughout the IAS and through the IAS mailing list. We hope that you will join us. Thank you.